The history of the theory of relativity is a fascinating journey that spans centuries and encompasses contributions from many brilliant minds, culminating in the revolutionary insights of Albert Einstein. This essay aims to provide a comprehensive overview of the development of the theory of relativity, detailing its origins, key milestones, and the profound impact it has had on our understanding of the universe. Early precursors and classical physics, ancient and medieval contributions. The seeds of relativity can be traced back to the early philosophical inquiries of ancient Greek thinkers. Philosophers like Heraclitus and Parmenides pondered the nature of change and the constancy of the universe, setting the stage for later scientific exploration. During the medieval period, scholars such as Alhazen and Al-Biruni made significant strides in optics and mechanics, providing a foundation for future theories of motion and light. The Newtonian revolution, the most significant leap forward in classical physics, came with Sir Isaac Newton in the 17th century. Newton's laws of motion and universal gravitation, published in his seminal work, Philosophiae Naturalis Principia Mathematica, 1687, provided a comprehensive framework for understanding the motion of objects and the forces acting upon them. Newtonian mechanics dominated the scientific landscape for over 2 centuries, describing the motion of planets, projectiles, and everyday objects with remarkable precision. The dawn of electromagnetism. Faraday and Maxwell. The 19th century saw the emergence of electromagnetism as a fundamental force of nature. Michael Faraday's experiments in the early 1800s demonstrated the relationship between electricity and magnetism, leading to the concept of the electromagnetic field. Building on Faraday's work, James Clerk Maxwell formulated a set of equations in the 1860s that unified electricity, magnetism, and light. Maxwell's equations predicted that light was an electromagnetic wave, propagating through the luminiferous ether, a hypothetical medium thought to permeate space. The concept of ether, the notion of the ether, was central to 19th century physics. It was believed to be the medium through which electromagnetic waves traveled, much like sound waves travel through air. The ether was thought to be an absolute frame of reference, against which all motion could be measured. However, this concept began to face challenges towards the end of the century. The Michelson-Morley experiment. In 1887, Albert A. Michelson and Edward W. Morley conducted an experiment to detect the relative motion of matter through the stationary ether. They used an interferometer to measure the speed of light in different directions, expecting to see variations caused by the Earth's motion through the ether. To their surprise, the experiment yielded a null result, suggesting that the speed of light was constant in all directions, regardless of the Earth's motion. This result was one of the key empirical challenges to the ether theory, and set the stage for a new understanding of space and time. The special theory of relativity. Einstein's 1905 Annus Mirabilis. The year 1905 is often referred to as Albert Einstein's Annus Mirabilis, miracle year, during which he published 4 groundbreaking papers in the Annalen der Physik, a leading German scientific journal. Among these papers was On the Electrodynamics of Moving Bodies, which introduced the special theory of relativity. Einstein's revolutionary work was based on 2 postulates. The principle of relativity. The laws of physics are the same in all inertial frames of reference. The constancy of the speed of light. The speed of light in a vacuum is constant and independent of the motion of the source or the observer. These postulates led to several startling conclusions that fundamentally altered our understanding of space and time. Relativity of simultaneity. Events that are simultaneous in one frame of reference may not be simultaneous in another. Time dilation. Moving clocks run slower compared to those at rest relative to an observer. Length contraction. Objects moving relative to an observer are shortened along the direction of motion. which states that mass and energy are interchangeable. Lorentz transformations. The mathematical framework for special relativity was provided by the Lorentz transformations, named after the Dutch physicist Hendrik Lorentz. These transformations describe how measurements of space and time change for observers in different inertial frames. Lorentz's work, along with contributions from Henri Poincaré, laid the groundwork that Einstein built upon, although it was Einstein who fully realized the implications of these ideas. The general theory of relativity. Einstein's further insight. While special relativity dealt with inertial frames of reference, it did not address the effects of gravity. Einstein spent the next decade developing a more comprehensive theory. In 1915, he presented the general theory of relativity, which extended the principle of relativity to non-inertial frames and provided a new description of gravitation. The equivalence principle. At the heart of general relativity is the equivalence principle, which posits that locally, in a small region of space and time, the effects of gravity are indistinguishable from those of acceleration. This insight led Einstein to view gravity not as a force, but as a curvature of spacetime caused by mass and energy. The field equations. Einstein's field equations describe how matter and energy influence the curvature of spacetime. These complex, nonlinear equations are central to general relativity and have been confirmed by numerous experiments and observations. The solutions to these equations describe a wide range of gravitational phenomena, from the orbits of planets to the dynamics of black holes. Experimental confirmations and developments. The 1919 Eddington expedition. One of the first major confirmations of general relativity came in 1919, when British astronomer Sir Arthur Eddington led an expedition to observe a solar eclipse. Eddington's team measured the deflection of starlight passing near the Sun, as predicted by Einstein's theory. The observed deflection matched the predictions of general relativity, providing a dramatic vindication of Einstein's work and catapulting him to international fame. Gravitational lensing and black holes. General relativity has since been confirmed by a multitude of experiments and observations. One of the most striking predictions of the theory is gravitational lensing, where light from distant objects is bent by the gravitational field of massive objects, such as galaxies. This effect has been observed countless times and is used as a tool in astrophysics to study dark matter and the distribution of mass in the universe. The theory also predicted the existence of black holes, regions of space-time, where gravity is so intense that not even light can escape. The first indirect evidence for black holes came from the study of X-ray binaries in the 1960s, and their existence was further confirmed by the detection of gravitational waves from black hole mergers by the LIGO and Virgo collaborations in 2015. Cosmological implications. Einstein's field equations also have profound implications for cosmology. In 1929, Edwin Hubble's observations of the redshift of distant galaxies provided evidence for the expansion of the universe, leading to the Big Bang theory. General relativity is the foundation for our modern understanding of cosmology, describing the evolution of the universe from the Big Bang to its current state and beyond. Extensions and alternatives. Quantum gravity. While general relativity is extraordinarily successful, it is incompatible with quantum mechanics, the theory that describes the behavior of particles on the smallest scales. This incompatibility has led to the search for a theory of quantum gravity that would unify general relativity with quantum mechanics. Various approaches, such as string theory and loop quantum gravity, are being pursued, but a complete theory remains elusive. Alternative theories. In addition to quantum gravity, there are several alternative theories to general relativity that attempt to address its limitations or extend its reach. These include modifications of gravity at large scales to explain dark energy and the accelerated expansion of the universe, and theories that incorporate additional dimensions or new particles. Conclusion. The history of the theory of relativity is a testament to human curiosity and the relentless pursuit of understanding the natural world. From the early philosophical musings of ancient thinkers to the groundbreaking work of Newton, Maxwell, and ultimately Einstein, the development of relativity has revolutionized our conception of space, time, and gravity. It has provided profound insights into the workings of the universe, from the smallest particles to the largest cosmic structures, and continues to inspire new generations of physicists in their quest to unravel the mysteries of the cosmos. Thank you for watching. Please subscribe our channel.